Alright, these are the problems that you can practice either on your own by pausing the tape and doing them on your own, or you can just do them with me. So if you just want to pause the tape now, you can. Now would be a good time. So I'm going to work through them, and hopefully you've either done them now, or you've done them already, or you're going to do them along with me. Now, if I'm going to write an equilibrium expression for this equation, remember K is my equilibrium constant, and it's defined as the concentration of the product raised to the power of its coefficient. So that's ozone squared, concentration of ozone squared, divided by the concentration of oxygen gas cubed. And that's that equilibrium expression. Now in the second problem, remember we cannot include solids, and we would not include pure liquids either, but we don't have a pure liquid here. The only thing we have that would have a concentration would be the gases. So again, the equilibrium constant is going to be equal to the concentration of the product divided by the concentration of the reactant. And in this case, the iron does not come into the equation at all. Number 3, I'm going to do right down here. The equilibrium constant is going to be the concentration of ammonia vapor raised to the second power times the concentration of carbon dioxide times the concentration of water vapor, all divided by, actually I'm not going to divide it by anything because this is a solid. So I'm just going to get rid of that line, and I'll move that down. I didn't even notice that the only thing on the left side was a solid, and that doesn't get written into our concentration equation, our equilibrium equation. So the fifth one, we're not going to write in the solid, and we're not going to write in that one on the other side. It might help if you just cross those out because they are solids, so you know not to put them in there. That way you won't make a mistake. So the equilibrium constant is going to be equal to the concentration of water vapor squared divided by the concentration of hydrogen gas raised to the power of 2, or squared. And that's it. Now there is something else that we need to add before we get into too much math with this, and that's called Q. So on the next slide, I'm going to explain what Q is. Now we can talk about the reaction quotient Q. Q is calculated when a reaction is not at equilibrium. It's done the same way you calculate K, but we don't call it K because K is the equilibrium constant. If it's not at equilibrium, then we have to call it something different, and that's what the reaction quotient is for. So in this example, butane will be converted to isobutane, and this reaction will proceed forward and backward, forward and reverse, until an equilibrium is established. So if they give you concentrations, like they do in this problem, isobutane is, the concentration of it is 4 molar and the concentration of butane is 3 molar, you can calculate a Q for this reaction and determine if it's at equilibrium. So you do this the same way that you did K. Isobutane, concentration goes on the top. The concentration of butane goes on the bottom. And I'm just going to substitute in 4.0 molar over 3.0 molar, and the molar over the molar just it's going to reduce itself to 1. So when I divide that out, I'm going to get 1.3. And you can see that this value does not match what is given for the equilibrium constant. Therefore, this reaction is not at equilibrium. All right, when Q, the reaction quotient, is equal to K, the equilibrium constant, when those two values are equal, the system is at equilibrium. And Q is valuable for us because it can tell us how a system is going to proceed to get to equilibrium. All right, so in this case, Q is not close to 2.0. It's got to go a little bit further. That means this reaction, because it is not, Q is less than K, that means the reaction, the forward reaction has to proceed a little bit more in order to reach equilibrium. You have to produce more products. So in this case, the system must produce more product to reach equilibrium. If Q is bigger than K, that means the system must go in reverse to produce more reactant. So we say in this case, the forward reaction is favored. Because you've got to proceed more in the forward direction, go this way to get more product, so this number goes up. If Q is less than K, that means the reverse reaction is favored. So that you're going to proceed in the reverse direction to get more reactant, the way the equation's written. So Q can be valuable to tell us what the system is going to do to reach equilibrium.